Hey, good morning, everyone. So, yesterday we had started the revision of the last chapter, Introduction to 4G. Um, so, yesterday we had completed the comparison of 3G and 4G, and we were here in the challenges and issue in 4G network. Although this question is not that important, uh, for this for the exam, but still, if the paper is being said by someone else, there might be a chance that this question can come. So what could be the challenge in fourth generation network? The first one is mobility management. And why mobility management is um, because fourth generation network is more scalable. It is everywhere in the world, everywhere in the globe, over the globe. So people are thinking that I can move from any location to any other location without any problem. And due to this mentality of a person, there are certain handoff that MSC has to do. Frequent handoff they have to do. And this frequent handoff is not very easy task. It is a lengthy process and a very complex process. So fourth generation network cannot handle that many handoffs that you are doing. You are constantly moving from one place to another place, and due to this, handoff has to be taken, and this handoff is very hard process for the fourth generation network. So this is our mobility management, which deals with the handoff technique. So what it says the handoff technique should be designed so that they make efficient use of network and make sure that handoff is not done that often. You can see here, right? So handoff should be very limited, and if you are doing it, then you should precisely drawn it out for the efficient use of network. This is the first problem. The second problem is basically deals with congestion control. So the congestion control, we have wired connection, and in wired connection, you know that I can detect and then recover, because it's a wire, and from the wire I can know that where is the problem. So in wireless connection, we I cannot detect the problem, because it is, uh, I cannot see it. It is a medium, as a air. So in air I cannot see where my signals are moving. So it is somehow really very hard for me to detect the problem, but certainly I can avoid the problem, right? So I need to avoid it to prevent the congestion. So if you are using wired connection as a fourth generation network, then you have to work with your flow control mechanism, right? Your flow control mechanism should be precise. That means your sender and receiver should not have the differences, much more differences. If your sender is using, very high connection, then your receiver should have a capability to handle that speed, that kind of flow from the sender. Okay, so both sides should be synchronization, on the data, on the speed. So if you are using wired, then you need to deal with flow control mechanism. If you are using wireless connection, then you need to work with your scheduling technique. That means access control. If I'm having five stations, then which first station is going to transmit the data, and after the first station, which is the second station is going to transmit the data. That allocation of time to the station is known as scheduling techniques. How you're gonna schedule the station to transmit the data is going to be handled by your wireless connection. With the help of this scheduling techniques, you can avoid the problem, right? These are some of the other things which are there in the uh, challenges or in the issues. One is multi-access timing and recovery. Uh, well, basically, it also deals with nothing but CSMA, your career sense multiple access. Then complexity is much more generated because of signal processing. There is more maths in fourth generation and in the next generation, that means 5 and 6 generation, more mathematics is being there. So it is more complex in error control and in the conversion from digital to analog or analog to digital. Then there is also one problem with the wireless personal area network, which is ad hoc network or Bluetooth or 802.11b. Your fourth generation network is not that compatible with your personal area network that you are creating. So fourth generation is not working precisely with Bluetooth or maybe with your ad hoc network. Then, of course, if you're using wireless communication, then security is the most basic problem, and that cannot be solved in an easy manner. So these are some of the challenges. You can see here that one, two, three, four, five, and six problems are there. You can elaborate in your own words. It's not that very hard, but I'm gonna make it bold so that you can find some relevancy. This is wired and wireless connection. So, and if you are using wired, then you need to work on flow control. If you're working with wireless, work on scheduling techniques, right? And then after that, we are uh, moving on to the OFDM, the most basic part of your WiMAX. So in continuity to the WiMAX application, this is the application. Uh, I told you that there is a base principle. On that principle, your WiMAX is working, and it is known as OFDM. And in this section, we're going to understand that what exactly is OFDM and how it is helping us. So any fourth generation network you will take, any fourth generation application you take, there is a base principle as OFDM. And OFDM is orthogonal frequency division multiplexing, which works on a physical layer of OSI. There is an alternative term for OFDM, which is known as MA, OFDMA, which is frequency division multiple access, which works on data link layer. I hope you know that there is a multiple access mechanisms, which is precisely there in the data link layer. So we are not dealing with OFDMA because it is different from OFDM. It works with something called as frame. Okay, you know that data link layer deals with frame. So we are not working with any frame here. So this part is not important, OFDMA. Okay, so we are working with OFDM only, multiplexing. So what is the reason behind this evolvement of OFDM? Well, the reason is very simple. It is because of we have FDM, and you can see here that uh, in your FDM, I have maybe like how much 100. It is of so I have four bands here, four carriers here. Let's say 1, 2, 3, and 4, and all these four carriers are having uh, frequency of 100 kilohertz. You can see here 100, 100, 100, and 100. So it is 400 kilohertz. But the problem is in between, in subsequent carriers, I need to make a gap, because if I do not provide this gap, this frequency is being interfere with this frequency. It means your 100 kilohertz of first carrier is going to interfere with your 100 kilohertz of second carrier, and this is not a good idea, because if I do this, then there is a small section of interference generated over here, over here, over here, and so on, which cumulatively being a very large effect on your complete signal, on your composite signal. If you take that interference level, it's very huge. So I need to remove this interference from the subsequent carriers. So in order to protect from this interference, what they did, they provide some gap. Okay, so there is a gap. Now this gap is completely depends on you, that or your application, that what kind of application you are generating or creating, sorry. So I have created a gap of 10 kilohertz, 10 kilohertz and 10 kilohertz. So cumulatively it is 30. So your complete FDM is consist of 430 kilohertz, where your 10 10 10 three times 30 kilohertz is your guard band, and 4 times 100 kilohertz is your actual carrier or your frequency. Now, if you observe here in frequency division multiplexing, these three gaps that you are seeing, uh, right now it is very small in effect. However, when you are having full-fledged signal or full-fledged composite signal, I hope you know composite signal. Composite signal is consist of many sine waves. It looks like this. So this is one signal, then second signal, then third signal, then fourth signal, and the same way, more and more signal will come, and this is known as composite signal. In general, in practical, single sine wave never goes. Okay, your complete signal goes like this, composite signal. So when you are having composite signals, there are many gaps like this. Okay, not only three, but maybe millions. So the cumulative effect, you can see that it is wasting my band. Right now it is 30 kilohertz, but if let's say 100, uh, I mean, half of the bandwidth is being consumed by this guard band only. Currently it is 10 kilohertz. Maybe someone had taken 50 kilohertz. Then you can observe that it is wasting my bandwidth. Half of the bandwidth is being taken by this guard band only. So it is not a good idea. So people who are working with communication or network communication, they thought that let's remove this guard bands, and let's these two carriers get interfere with each other. Okay, so they just remove the guard band in the OFDM, and they just make these carriers as it looks like interfering, but they have created something called as orthogonality in between these two subsequent carriers. Okay, so उन्होंने क्या किया कि इन दोनों carriers में orthogonality generate करवाई है. So you know from the engineering graphics that orthogonality is like something like this. So if this is the one signal, then from the front it looks like it is starting from here, but actually it is just behind this, just behind this signal. Okay, just like this. It is orthogonal. It looks like this. Okay, from the front it looks like they are interfering. It is something like this. It is interfering, but it is not. So they have created this OFDM with a maths component here, this orthogonality, which is so it is OFDM, and they removed this guard band and let's these two carriers get interfere. However, it is not. And due to that, what happened? This OFDM is not wasting my bandwidth. It is totally it is not wasting any bandwidth, but it is actually saving my bandwidth. Here 30 kilohertz is wasting. However, because we are overlapping these subcarriers, some of the bandwidth is being saved here. Okay, this 30 kilohertz, which is eventually wasting, here 30 kilohertz is somehow saved. Okay, and that's why it is good. So it has been said by the people who have generated this OFDM that half of the bandwidth is being saved in OFDM. So it's a good thing. And the next thing is again the carrier part. So what traditional FDM says, so here you can see that this whole carrier is only single carrier. You can see here, this is a single carrier. It is using the complete bandwidth. Okay, so if I am giving 100 kilohertz here, then this whole carrier is of 100 kilohertz given to some specific user. Okay, here you can see here. Okay, so if this is a bandwidth of 10 megahertz, then this whole carrier is of 10 megahertz and it is given to some user. However, in the recent OFDM, what will happen? This has been divided, this whole carrier has been divided into small segments or small sub carriers. So now your 10 megahertz has been divided into number of sub carriers. So your bandwidth is divided by n. So n, if is like I want to divide by 1000, then n is going to be 1000. So now these small segments you can see here, they are of 10 kilohertz. Okay, so now I can use this 10 kilohertz to some specific user, 10 kilohertz to some specific user, 10 kilohertz to a third person, or 10 kilohertz to a fourth person. Here it is not like that. A person is being allocated complete 10 megahertz. Maybe sometimes he is not using 10 megahertz. Okay, so maybe like if I am giving like 10 megahertz उसको पूरा दे दूं मैं, तो पूरे 24 घंटे में ऐसा तो नहीं होगा कि वो 24 से 24 घंटा इंटरनेट यूज कर रहा होगा, राइट? सो यहाँ पर मैं वेस्ट कर रहा हूँ पूरी की पूरी, कुछ देर के लिए वो नेट यूज करेगा, लेकिन 10 megahertz इज अ वेरी हाई गुड फ्रीक्वेंसी एंड आई एम गिविंग complete 10 megahertz to a specific user, wasting. Here I'm using only 10 kilohertz to a user. Small frequency उसको जब यूज करना होगा वो करेगा, otherwise यहाँ wastage नहीं होना है. So this is your recent OFDM that has been evolved in contrast to FDM. Now, do you have any specific doubt in here? Then let me know. Any question, any doubt, any problem? Okay. Uh, the next part is basically how this, there is a problem in FDM known as interference, as I told you here, and then how basically FDM has been resolved. It is nothing but this subcarriers is actually resolving the errors, sorry, interference. So simply you can observe here there is a bandwidth of 10 megahertz, and this complete 10 megahertz is being used by one single user. So therefore n is going to be 1. There is something called as symbol time. T is equals to 1 by b. That means how much time is being taken by one symbol to be transmitted from sender to the receiver, right? Symbol time. So symbol is nothing but a kind of um, one sequence of character. Okay. So T is equals to 1 by B, and B, it is 10 megahertz. So I just had placed it 10 into 10 is to 6, and you will get a 0.1 microsecond as an answer. So your symbol time is 0.1 microsecond. That means one symbol is taking zero point 0.1 microsecond in transmission. It means from sender to receiver. Now you know that when I'm using wireless communication here, just like this, here, something like this. This is actually the channel, and you can see that every channel has has a delay component. So this channel here that you are seeing here, this channel is actually having small or minuscule delay. Delay is why? Because air has a friction, gravitational force, and so many other obstacles, and that's why I have some delay in the channel. Okay, so you can see that that delay is been assumed as 2 to 3 microseconds. Now the problem is what? Your symbol time, that means transmission time, is actually very less than the delay. If you can understand that if my transmission time is very small, very, very small, then the delay, and your delay is very, very large, then definitely there is a problem. And that problem is nothing but a kind of interference. Okay, we say that there is an interference problem. We generally say it as like constructive and destructive interference. You do not need to remember, but it is interference, let's say. So this is a problem. Now, what happens in OFDM as my bandwidth is being divided into subcarriers? So let's say my n is 1000. So my equation of bandwidth is going to be changed. It is not the complete bandwidth now. It is divided. So that's why I have b by n. So when I place this t is equals to 1 by b, so it is not b, it is b by n. So it is going to be t is equals to 1 by b by n. And I change it to n by b reciprocal. When I place the subsequent values, I get a symbol time of 100 microsecond. Now that means my transmission time is now 100 microsecond and channel time is 2 to 3 that we had assumed. Here the symbol time is actually very, very large than that of delay, and it is good. Okay, and therefore the OFDM is resolving the problem, not only interference but any error problem. This is basically the idea that why OFDM is better than FDM. This is not that relevant, but if someone asks you that how interference has been resolved in OFDM, you can explain with the help of these two comparison. Okay, so next is a block diagram of the division multiplexing, that means OFDM, and this is actually very important. Um, so again, the same thing. I have a transmitter, and I have a receiver, and then again I have a channel. So if some person wants to send something to the receiver, then the data is being uh, uh, from the analog to the digital, or the digital signal is being converted with the help of this random source. You can see that if some person is speaking something, maybe hello, so the hello is being converted into 1010 with the help of this random source. Then this 1010 is in serial form. This serial form is going to be converted into parallel, is going to be converted into parallel with the help of serial to parallel converter. So you can see your serial is being converted into parallel. Now why serial to parallel converter? Because um, in order to in order for fast calculation. So if I send the data in this manner, what will happen? In the for the maths, it is very hard because your data is now in this manner, and continue and continue and continue and so on. It is very hard for me to calculate, observe, view, very hard. But now if I do something like matrix, so like this, like this, like this, if I have matrix of several boxes, then it is somehow hard for me to calculate it. It is really very, very simple for me to analyze it and calculate it. And that's why I have serial to parallel converter. So this serial data which is coming here is being converted into several parallel component. Okay, here. That's why I have a serial to parallel converter. And this serial to parallel converter will create a matrix, maybe 3 by 3 cross 3, or maybe 4 cross 4, likewise. And then that matrix is being forwarded to something called as symbol mapping. Now, yesterday's lecture, I told you about symbol mapping. Anyone remember what do you mean by symbol mapping? Anyone who remember a symbol mapping? Many of you were there in the yesterday's lecture. If you remember, um, symbol mapping. Okay, no issue. So symbol mapping is actually it is modulation. It is a modulation, and you can observe here that it is written QAM. It is written. It is quadrature amplitude modulation. So now what will happen is that I have a data of 1010. It's a digital format data, um, and I cannot send this data like 1010. I cannot do that. I need to map it. I need to modulate it one by one. Every single bit needs to be modulated with the help of this symbol mapping. So I'm gonna use something called as QAM, and QAM is going to give you some complex number. So earlier it is natural, it's nothing but a digital number, but now it is converted into something called as complex number. So one is going to be now look like 1 plus ij. I do not know, but I think complex number look like this only. 0 plus ij, 1 plus ij, 0 plus ij likewise. Okay, and why it is there, why I'm changing it to complex number, because it is important for the IFFT block. Okay, IFFT block needs an input. This is the input, and input needs to be a complex number, not a 1010. It is not going to be accepted by this IFFT block. Very hard. So I need to change this 1010 to a complex number with the help of QAM, quadrature amplitude modulation. So that's why I have a complex. All these 1010 is going to be changed to 1 plus ij and 0 plus ij. So all metrics, okay, by terms of metrics is being converted. Um, I Okay, so these blocks are actually hardware, by the way. If you think that, sir, what is this block? Block are nothing but hardware. They all are these hardwares, okay? And this line is actually input and output. So this is the input and this is the output. So input needs a complex number, okay? Now, this complex number is now forwarded to IFFT block. And if you remember, IFFT is the inverse fast Fourier transform. It is IFFT. And if you know that IFFT basically converts the data uh, into the time domain. So the frequency which is coming with this data, the frequency domain signal is now converted into time domain signal. Okay, so frequency domain signal into time domain signal. So if you do not remember frequency domain and time domain, I think I have a diagram. Yeah, this one. You can see here that this is a frequency domain signal, 5 volt. Uh, it's a frequency domain. With the help of IFFT, this 5 volt is now converted into time domain signal. And in the oscilloscope, it looks like this, one single line. Okay. In oscilloscope, frequency domain look like this. In oscilloscope, time domain look like this. Okay. Same, 5 volt. This is again 5 volt. So this is IFFT, which converts your frequency domain signal into a time domain signal. Now that block, that metric block is now move on to the cyclic prefix, CP. And what this CP is, this is CP. So suppose that you are sending, I'm not taking an example of 1010s, but I had taken 1, 2, 3, 4, 5, no issue. So 1, 2, 3, 4, 5, if you want to send from transmitter to receiver, um, but the problem is if you just send 1, 2, 3, 4, 5 without CP, then your channel is basically very noisy, right? It is very noisy channel, and due to that, what will happen? This 1, 2, 3, 4, 5 maybe get lost, okay? Maybe get uh, maybe just get deleted or maybe get errored. Some problem happens to this 1, 2, 3, 4, 5, and Because of that reason, to protect this data 1 2 3 4 5, this CP is going to copy some of the bits, whatever you give to the CP. So if you give CP is equals to 5, then the very first 5 bits is being copied to the last part. So if I have 1 2 3 4 5 6 7 8 9 10, and if you give CP equals to 5, then 5 bits is being copied from the first frame and pasted to the last frame like this, right? So now you can see here that this 1 2 3 4 5, and then again duplication 1 2 3 4 5 is now going to be entered into the noisy channel. And if some problem occurs, then somehow 1 2 is being lost, but still I have a copy of 1 2. If 1 2 3 is being lost, again I have a copy of 1 2 3. So then there is no issue with that. Okay, so that's why I have a CP. It's a cyclic prefix, and that is the reason why we have used the CP. Then the block is going to be forwarded to the parallel to serial converter, and I you know that I cannot send the parallel data to the receiver. It is non-readable format, because your receiver will not understand the data if you send it in the form of matrix. So again I need to change it to the serial uh, for the transmission. So I send to the block known as parallel to serial converter, so that your metric is converted again into the serial format. Then it forwarded to the noisy channel, and the all problems happen here, occurs here. Then the data is being received again to the receiver part, and all the functions that you did in the transmitter, the reciprocal of the transmitter is going to be happen in the receiver. So parallel to serial converter is having serial to parallel converter. So your parallel data, serial data is now converted into parallel. Move on to the remove CP. So CP is equals to 5 that you had provided here is now deleted, is being removed. So these extra, the duplication is being now removed. Otherwise, what will happen? Uh, this will take your all bandwidth. Okay, so data को send हम डेटा सेंड करना चाहते हैं, लेकिन उससे ज्यादा हम यहाँ पर डुप्लीकेशन सेंड कर रहे हैं. सो मुझे उस सीपी की वैल्यू को हटाना पड़ेगा. सो दैट्स व्हाई I have a remove CP. Then the data move on to FFT, and FFT is nothing but a conversion from time domain signal to the frequency domain signal again, right? So uh, I had changed from a time domain signal to frequency domain signal. Again, it is fast Fourier transform. So the frequency domain signal move on to symbol D mapping, where all these complex number is being removed. 1 plus ij is now converted into 1 0 1 0 1 0 and so on. Move on to parallel to serial converter. Your parallel data, it means metric data, is being converted into serial form. That means 1 0 1 0 1 0, complete serial line, and then received it to the receiver. This is a complete block diagram of OFDM. Now, any block that you do not understand or any problem with OFDM, please let me know. Okay. Okay, yesterday there are many other students joined who have not joined yesterday. So any, let me see, Harsh, I do not know about Harsh. Harsh, have you completed your assignment 1, 2, and the Cisco? Yes, and, I think Heath is also not there yesterday. Heath, have you completed all these three things? Signal was there. Kunal, uh, have you completed assignment one, two, and okay, nice. Mansi, Mayank, Nish, you have completed one, two, and Cisco. And about Neeldeep completed. Okay, Nishant, I think Nishant was there, no issue. Palak was not there. Palak, have you completed the assignment one, two, and Vidhi was there. Sagar, what about you? Sharon, Tumin, and okay, Tumin is done. Uh, and Yug, okay, okay, great. I do not know why less number of students joined. I mean, it's I think 5 months we had taken for this subject to complete. Um, of course, it is boring now. After that, okay, so this is application. Okay, so channel. Okay, so these are the application. Actually, I think these application is given by you only as a task. So if the question comes up like explain the applications of fourth generation, then just do not give. If this is a 1 mark question, then you can list. Okay, you can list these applications like these 10 applications. But if the question is of 4 marks, then make sure that you specifically describe this, what is a multi-mode software application, mobile gaming, real-time traffic conditions, and so on. You need to give the explanation of these applications. If it is like 6 marks, I do not think that this comes in 6 marks. But hello, if it is coming in 6 marks, then please explain all these the explanation of these applications. It is very important. Then what is this? It is error correction and detection, and why it is here. I do not know. It is there in the chapter or no? Okay, yeah, so this is also there. It is error correction and error detection. Um, it is channel coding actually. So I have not provided you all the code. Uh, I'm giving you only one convolutional code. And sir, why you are giving is because in your YMX there is a channel coding, I think. Yeah, there is. So this channel coding is having different coders. So one coder I had explained you here in the in this chapter. So this is convolutional code. And this convolutional code says it is having a hardware device. This is a hardware device, and in this hardware device there are three registers which stores the bits. So it depends on the hardware. I mean आप किस तरीके का hardware ले रहे हो. ये 3 का भी आता है, 4 का भी आता है, 6 का भी आता है, लाइकवाइज ज्यादा नहीं होते, 3 4 ऐसा कुछ ही होता है. सो मैंने 3 का लिया है यहाँ पर, और इन 3 रजिस्टर को मैंने नेम दिया है M0, M1 and M2. And then I have two other values as x1 and x2, which gives the output. So these are inputs and these are outputs. Okay, and all these components are being connected with some wires. So your M0 is being connected to x1 and x2, and M1 is connected to x1 only, and m2 is connected to x1 and x2. Okay, so for the from the x1 and x2, x1 is going to be m0 plus m1 plus m2, and x2 is actually m0 plus m2. Remember, this x1 and x2 is going to perform XOR operation. Okay, so the output that x1 is going to get is actually the XOR of m0 XOR with m1 XOR with m2. The same way x2 is having output with the help of m0 XOR with m2. So now what will happen? Your m0, m1, and m2 initially uh, having 0. So I have not provided the 000. So suppose that there is a data of 1101, 4 bits I want to send, and what will happen is because is that this 4 bits is being stretched out to 12 bits, okay, or more bits. And why more bits I want to add? So that I can add some redundancy, and this redundancy will let you precisely detect the error. Okay, I want to stretch out my data bits. Okay, डेटा बिट्स अगर मैं सिर्फ और सिर्फ डेटा बिट्स को सेंड करूंगा तो मैं एरर डिटेक्ट कभी नहीं कर सकता हूँ. एरर डिटेक्ट आप कब कर सकते हो? जब आपके पास कुछ एक्स्ट्रा बिट्स हो एरर को डिटेक्ट करने के लिए. सो मुझे वो एक्स्ट्रा बिट्स ऐड करनी पड़ेगी. अब ऐसा नहीं है कि आप कोई भी बिट्स ऐड कर दो और मेरा एरर डिटेक्ट हो जाएगा. नहीं, आई नीड अ प्रिसाइज मैकेनिज्म फॉर दैट, एंड दिस कॉन्वोल्यूशनल कोड इज अ प्रिसाइज मैकेनिज्म. सो यू कैन सी हियर कि सबसे पहले मैंने क्या किया, m0 m1 पे 00 है, m2 पे मैंने ये पहला वाला 1 ऐड करवाया. I think this one. I do not remember the order, but this one is being added. Now I did the conversion of XOR. This is the XOR conversion, and get an output of 1 1. Now what will happen? This 0 is going to be shifted. It is been removed, and this 0 is being shifted here, and this 1 is going to be shifted over here. Then this one, I think this is the order, I guess. So this one is now come up here, and XOR operation will be performed, and then again this 0 is being removed, this 1 is going to be shifted, and then this one is going to be shifted, and 0 will come over here. This operation you need to perform till 000 comes up, and you will get an output of 00. So when you get a output, when you complete this, you will get the output like this: 110101001011. You can see this 4 bit is now stretched out to 12 bits, and these extra bits will let you detect the error, and later it can be correct the error. So this is actually convolution code, which is actually not very important for the syllabus, but in Biomex your channel coding is there, that's why I had provided. Okay, so this is the chapter. Okay, so one by one मुझे बोलते जाओ क्योंकि I only have 21 students. So Ayush, what is your number? I think it's 49 or 40, 49. Okay, done. Daria, what is your number? 77. Okay, Harsh Marthak, 190. Heth, okay. Zinal, 06, okay. Komal, 18. Kunal, 76. Lata,
Yes, sir.
what number?
17, sir.
17. Right. Mansi, 62. Mm, Mayank is Mayank 1. Okay. Nesh is 41. Neeldeep, 69. Nishant, 60s. Palak, Riddhi, 66. Okay. Rutvik, 79. Sagar, 16. Sharon, 70. Tumen, 7. And Yug, I think it's 119. Yes. Okay, then. I think no one is left, right? Okay, then. Thank you so much, guys. Thank you.